In the previous lecture, we started analyzing circuits with capacitors. And the same thing will apply to inductors as well. And the result is that we have to solve a differential equation. Okay. If you have a single capacitor, we will end up with a first order differential equation, and the solution to that turns out to be some exponential response. That is the solution to the homogeneous part of it. And if you have a constant input, the steady state response is also a constant. Okay. And the total solution is the sum of steady state and natural response. The natural response is an exponential. The steady state response for a constant input is a constant. So combining these, you can find the total solution. And so the total response is the sum of steady state and natural responses. And the natural response comes with some unspecified scaling factor, because that response will satisfy the homogeneous equation with any scaling factor. So the particular value of the scaling factor has to be found from initial conditions. Okay. Now with the capacitors, you have this property that its voltage cannot change instantaneously if the currents are finite. So that's how you find the initial conditions. Okay. So for instance, we took this circuit where there is a constant Vs applied to this combination of R and C, and this Vc has some initial value at t equal to 0, and the total response turned out to be we could write it in many different ways. Okay, where this is the steady state or force response, or the particular integral as it's called in the literature on differential equations. And this part is the transient response. Transient obviously means that it is short lived and it will go out eventually, or the natural response, meaning that this is some property of the circuit by itself, not the input that you applied. Okay. Because you have a particular value of R and C, there is an exponential with a certain characteristic, okay, with 1 over RC in the argument. That's what gives you the natural response, or you can also think of it as the solution to the homogeneous equation. Okay. And the other way of dividing it up is to group all the terms with Vs and the terms with the initial conditions, and you call this the zero state response. In this case, the word state applies to the voltage on the capacitor. The voltage on the capacitor can have a certain value, okay, based on its history. That's what the state is, okay. And this is the zero input response, okay. So you can think of these two expressions as here where you have the steady state solution, but there is some residue, which is the difference between initial and steady state. That part decays with time. Or this also is illuminating, in that this you can think of as the source voltage building up to its final value, that is this 1 minus exponential, and the initial condition decaying off. Okay, so that's the interpretation of these parts of the solution. Okay. In this particular case, we saw that the transient response or the natural response always dies out, right, because of that exponential with a negative argument inside it. It always goes to 0 as t tends to infinity. So you will be left with the steady state response. Now this is a property of what are known as stable circuits. Pretty much every circuit that we will consider in this course will be a stable circuit. So that means that finally you will have a response which is equal to the steady state response. Okay. This, of course, all these apply with constant inputs. I mean, if you have some Vs of t, you can't substitute Vs of t into this formula. Okay. Now this can be a model for something like this, where you can say Vs changes from some value, let's say 0 volts to 5 volts. Okay. So essentially there is a step change in Vs that also falls in this category. So when I say Vs is when I say a constant input, it can be piecewise constant, because let's say you have a step here. So you note down the value of this capacitor voltage just before the step. Okay. And in this case, infinite current cannot flow through the capacitor, so that value will be preserved just after the step. That will form this Vc of 0. Okay. If we define this instant to be t equal to 0, that will be this value of Vc of 0, and this other value, this 5 volts, will be Vs. Okay. So you can find this, and let's say after some time this Vs changes from 5 volts to minus 3 volts. How would you find the solution then? So again, the way this equation is written, you have to redefine this instant as t equal to 0, but you get the idea. You have some value of Vc just before this step, and you use that for this Vc of 0, and the final value of this minus 3 volts, that is what you use for Vs. Okay. So when I say constant, it doesn't have to be absolutely constant. It's, as long as it's piecewise constant, you can work out things piece by piece. Okay. Is this clear? So it's pretty obvious that what happens is, let's assume that the capacitor voltage initially was 0, then it will start rising up. Maybe it doesn't reach all the way to 5 volts, but you can compute what that is depending on the amount of time that is elapsed, and then it will start heading towards minus 3 volts. And if there is a step change again, it will change in some other way. Okay. So for arbitrary piecewise inputs, you should be able to find the response of a circuit like this. Okay. Now this kind of solution also applies when it's the same type of circuit but looks very slightly different. So let's say this is now a constant, a DC source, and you have R and C, and you must have seen problems of this type where the switch is either open or closed at some instance of time. So before t equal to 0, whatever voltage is on the capacitor stays as it is, because no current can flow through the capacitor. That's an open loop. And when t equals 0, this switch is turned on, and you get this Vs, R and C in series, exactly the same circuit as we had before, and the solution will also be the same. So the value of Vc of 0 will be whatever was on the capacitor before you close the switch, and Vs is the value that you apply. Okay. So that's exactly the same thing applies, and you could have lots of variants of this. I mean, instead of this closing like this, you could have some other switch that is opening and then something else closing and so on. Okay. So you should be able to solve any problem of this type as long as you have only one capacitor. That is important, because so far we have learned how to solve differential equations of first order, right? And this is known as a first order circuit. A first order circuit is nothing but something that follows a differential equation of first order. Okay.